Hey everyone, my name is Schlottke-Lakemper, and together with Ranocha, we will be sharing some of our experience with scaling Trixi.jl to more than 10,000 cores using MPI. Before we get started, I would like to acknowledge the great Trixi.jl community. There are a number of people here on that list without whose contributions the results that we're presenting here would not have been possible. So first of all, what is Trixi.jl? Trixi is an adaptive high-order simulation framework for conservation laws, obviously written in the Julia programming language. We have three major design goals. First of all, this should be an extensible code useful for our own research. It should be usable enough that we can also do projects together with students. And of course, performance is a major issue. Trixi is integrated within the Julia ecosphere, and we make use of a number of packages, for example, ordinary diffq for time integration, polyester for multi-threading, and of course, MPI-JL for distributed parallelism. So what are the kind of simulations we're running with Trixi.jl? What kind of numerical methods can you use here? This is a simulation of a supersonic flow coming from the left. There's a little obstacle here with this little cylinder here. You can see there are curved walls. So we have a high order in space and time discontinuous JuliaCon method. And we use adaptive mesh refinement, as you can see in the lower left corner here. So the mesh adaptively refines where something interesting is going on in the solution. Another example of what the kind of simulations we're looking at is the shallow water equations. This is a simulation of a flooding event in the seaside town of Seaside in Oregon. We use real-world data here to model the geography here, and we can predict how the water in case of a flooding event would distribute and flow back. So these are just two examples of the kind of simulations we can do with the Trixi.jl. But today we want to talk about parallel performance. And before we talk about parallel performance, we have to look at serial performance, of course. So for this, this actually results from a paper that we already published 2 years ago. This is a 3D compressible Euler simulation setup for the envisaged Taylor-Green vortex. We use a curvilinear mesh with entropy conservative fluxes. So this is only relevant if you care about discontinuous JuliaCon methods. And to evaluate the performance, we compared it against a Fortran-based simulation code that is already very mature and optimized. It's called Fluxo. And when we look at the result, we see here a number of curves. In this plot, lower is better or lower is faster. And we see the top curve here, that's Fluxo. For a number of polynomial degrees, we're looking at the time per right-hand side and degree of freedom. So less time is better. The Trixi baseline curve is in green, so this is basically where we started off. And then we, in this paper, we put in a lot of effort into further optimizing these methods, and then we ended up with this blue curve, which was even better than the original implementation. So the key takeaway here is that Trixi.jl is a fast serial solver, and that, as usual, we do not claim that Julia is somehow faster than Fortran, but that the actual performance really is only dependent on how much time you spend optimizing your code. So before we started with the parallel scaling experiment, we had one thing in mind, and that is the memory usage in Julia. So we've noticed that the Julia memory usage has been increasing since Julia 1.6. With each new Julia release, the memory usage goes up. And this is a plot for the maximum residence set size after certain operations done in Julia and for different versions of Julia. So we're looking at 1.7, 1.8, 1.9, and a pre-release version of 1.10. Disclaimer, with the final 1.10, the numbers will be different and probably a little bit better, but this was when we did this.
Ich weiß nicht, wie.
These were the results.
I don't know how good my connection is, so we'll see.
Yeah, sure. At least I should be able to stay in here.
Okay, it's great that you made it.
Hey guys, do you hear me? We are already watching your video, so it would be good if you won't speak for the next couple of minutes. Sorry for that. Talk to you in a second, but great to see you and great that you're here.
Sorry.
And as we can see, with each new release, the memory usage grew. So this is the baseline usage. Then after using Trixi, we're already with Julia 1.9, for example, at roughly 800 megabytes of memory usage. Using ordinary diffq pushes this to 1200 megabytes, and then running a simple simulation to almost 1.5 gigabytes. So while this is okay, sort of okay-ish if you have a hybrid code that uses MPI and threads or GPUs, that's problematic for MPI-only parallel codes. And this is actually what we wanted to do in our numeric experiment. So for our parallel scaling, we used the Eureka supercomputer at Jülich Supercomputing Center. And this has a very nice property that on each compute node, which consists of 128 cores, we have per node, we have also 4 gigabytes of main memory per core. So even when you look at the memory, the high memory usage of Julia, there's at least roughly 2 to 2.5 gigabytes of memory available for the application itself. So basically excluding the Julia memory usage. All right. So for this is the first parallel scaling result we got. This is a strong scaling experiment on Eureka with Julia 1.8. Strong scaling means we have a fixed problem. We start with a low number of ranks. So we have 128 ranks on one node, so one rank per one MPI rank per core. And then we take the same problem size and just distribute it over more and more nodes and more ranks, and see how the performance works out. So this has roughly 17 million degrees of freedom. And as we can see, we have a good scalability to 16,000 to roughly 16,000 ranks. In this case, higher is better. Here we're looking at the number of degrees of freedom updates per second. And as we also can see that Trixi has a near linear scaling on this scale, and a similar result is for the Fluxo code. We can also see that Trixi is slightly faster than Fluxo, but this is not a surprise. We already saw that it is slightly faster in the serial case. The key takeaway here, however, is that again, we have a comparable performance as the Fortran-based Fluxo code. And especially in the CFD world, Fortran is still the major workhorse language for high-performance computing. So we cannot expect to be better than Fortran, but if we are as good as Fortran, this is a very, very good result for us. So, of course, we also wanted to go to higher core counts than 16,000. However, we investigated and looked a little bit at the startup latency. As you all know, Julia is a just-in-time compiled language, so you have some sort of startup latency. And we looked at things like compilation time and code loading time. And up to 2,000 ranks, everything actually was quite nice. So you see different curves here. For example, orange curve is compilation time. And for example, the purple curve is using ordinary diffq. That stayed fairly constant. But with more than 2,000 ranks, the purple curve started to grow quite fast. So with 16,000 MPI ranks, we're already at more than 10 minutes of waiting time just for executing the command using ordinary diffq. So obviously parallel becomes a bottleneck. And if we want to go to higher core counts, this is not going to fly anymore. I mean, we're just burning CPU hours doing I/O, or basically waiting for I/O. So we had to come up with a solution. And the idea was to create the Julia depot in the RAM drive. So basically trigger pre-compilation on your compute node, on your login node, sorry, then tar the depot. And then when you do a parallel job, you just take the entire depot, upload it into your node local RAM drive, and then just be happy about it. And this actually worked quite nicely. When we now look at the purple curve, we can see the dashed curve is now with the RAM drive. The continuous line is the original curve that you just saw before. So while the original curve, the loading time goes up sharply after 2,000 ranks, we now have a very nice, flat, constant loading time when we do using ordinary diffq. So problem solved. And now we were able to do a scaling to a much higher node count. Actually, we used the same setup as before. We just increased the initial resolution. We're still using the invisible Taylor-Green vortex, but now with 134 million degrees of freedom. And we can see, again, we have good scalability from 128 cores to over 60,000 MPI ranks, which is the full Eureka machine. So we were not able to scale this any higher on this machine. Still, it's a very nice 400x speed up. And at the high core count, we actually have only 34 DG elements left per MPI rank. So what are the conclusions? First of all, I introduced Trixi as an extensible, usable, and fast framework for numerical simulations. We were able to show that we can get good parallel scalability to more than 50,000 cores. And the key takeaway message here is that, yes, Julia is capable of doing HPC computations also in traditional HPC applications like computational fluid dynamics. The serial and parallel performance is similar to Fortran, so there's no reason to not use Julia for these kind of workloads. Although there is a small caveat, there are still some challenges, for example, the startup latency, but there are ways to work around it. In the future, we're of course trying to push this scalability to a little bit further to go to more than 100,000 cores. We also want to look specifically at other ways how we can reduce the memory usage to also do this on other machines, and we want to look at GPU computing. So thank you very much for your attention. I'm happy to we're happy to answer questions, and if you have some questions later, you can always reach out to us via our GitHub webpage. Thank you very much.
I'll go ahead and ask my question. That's fantastic work, by the way. Very, very impressive to be able to do fluids HPC in Julia like that, comparably with Fortran. But now, how about the software end of it? What's the how is the Julia as an improvement to Fluxo in terms of development time, comprehensibility of code, flexibility? What are the pros?
I'm not sure if you understood the question, so let me repeat it. The question sort of is, what is the improvement of Trixi compared to Fluxo when it comes to development time, comprehensibility of the code, so the software aspects?
Maybe I can take this question. Thank you for repeating this. And first of all, I'm really sorry that we were not able to make it in person to this conference. So in terms of usability and in terms of features, I think these are two pairs of shoes. However, one thing that we noticed from early on is that when we started developing Trixi, it was extremely easy to get students interested in working on that code. And it was also it was very easy to get other researchers working on this code, because it was just so much easier using the modular approach that Julia allows one to use for such kind of simulation softwares, that other people could, just focus on a particular bit of the code and then try to change it, put in some new physics, put in some new numerics, and then see if it works. Whereas with the old code, which is still a very capable and state-of-the-art research code, it was much harder to get students to the point where they could contribute meaningfully to it. Does that answer the question?
Yes, it does. Thank you.
How about line count or something?
Just one follow-up question. What about line count? Can you comment on that?
I think line count is hard to compare because we use different paradigms for Trixi than we used for Fluxo. So, for example, Fluxo is inherently a 3D code, whereas in Trixi we also support 2D and 1D computations. So that, of course, changes a little bit. Also, I would say that because in Trixi, from the very early on, we said we want to be able to easily extend it with new features, try out new things, And even if they work only with a subset of the existing methods, we will accept them if someone finds them usable. In Fluxo, this is a little bit different. So in Fluxo, everything has to work together with everything else. So this also changes this a little bit. Overall, however, I would say that the line count in Trixi is probably a little bit lower than it is in Fluxo.
All right, thanks for the answer. Any other question? There's one more from Johannes.
Hey, actually, can you hear me? Okay. So you were staging to temp, and I'm curious, did you try a container runtime, and if so, what were your experiences?
So question is, did you try container runtime? What were your experiences if you did?
No, so far we have not tried to use Trixi.jl within a container runtime. No.
I have a question. I can go here. You mentioned parallel I/O. What are you using currently for parallel I/O?
At the moment, we're still relying on HDF5.jl. Because we had prior experience with that, and admittedly, it has not been our main focus so far. Because as you saw from this presentation, we're just getting into that regime, beyond 10,000 MPI ranks, where parallel I/O becomes really a key issue. So we're just starting to dig into this. One thing I definitely want to try out is to have a look at Adios 2, maybe, because I think it can help us in a few areas, but I haven't done this yet.
Don't. No, actually, no.
He
Yeah.
said don't. If you like.
No. Actually, do it.
All right. Anyway.
Well, sorry.
Go ahead, Michael.
No, I just mentioned IDSO because I have a good connection with one of the key developers of the Julia package, so I thought that might help.
Yeah, I'll contact Eric. So.
You'll contact Eric. Good. Thanks, guys. Thanks for answering the questions. Let's thank the speakers again.